In 2.1, we look at operations with matrices. So to begin with, let's just, we've done things with matrices before. Sometimes when you name a matrix, sometimes you just name it by giving it a letter, matrix A, matrix B, matrix C. Sometimes you'll put in brackets and you'll put elements of that matrix, a certain representative matrix. But two matrices are said to be equal if all of their corresponding components are the same. So for matrix A and matrix B to be the same, the row 1, column 1 component, the row 1, column 2 components, yada, 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 those all have to be the same. Which also should let you know that the matrices have to be the same size. Remember, we described the size of a matrix by its row and column. So this matrix has 2 rows, 2 columns. So we would have to have another one with 2 rows and 2 columns to be equal. Now, sometimes you might hear something referred to as a column matrix or a column vector. And all that means is that you have a single column. So an example of a column matrix or a column vector is as such. If you think about a two-dimensional vector, that could be its I hat and j hat components. Could be what that represents. So it's just a single column. Also, we have things called row vectors or row matrices, and it's the same thing except with a row. If you have a single row, that's a row matrix or a row vector. So in order to add two matrices together, they have to be the same size. If A is a 3 by 2 matrix, then B would also have to be a 3 by 2 matrix. And the reason for that is the way we add two matrices together is we add corresponding components. If I have vector 0, 3, -2, 4, and I want to add that to matrix 1, -1, 2, 1, then I take the row 1, column 1 components and add those. The row 1, column 2 components and add those. Row 2, column 1 components. And then row 2, column 2 components. So this, if we call that matrix A, that matrix B, that's the sum of those two matrices. So it's basically the same thing you'll do when you add two vectors together. Here you could think about this as having two columns or two different vectors here and two different vectors here. We're adding these vectors and these. But in terms of matrices, we're just adding corresponding components. Just like with vectors, we can multiply a matrix by a scalar. So we can take some matrix A, multiply it by a scalar. So let's suppose A is 0, 3, 2, -1. If we want to multiply that by the scalar -2, then each component gets multiplied by that scalar. So -2 times 0, -2 times 3, -2 times +2, -2 times -1. So just multiplying each component together. Now we talked about addition. If we wanted to do subtraction of two matrices, it's subtraction and addition are basically the same thing. They're just opposites of each other, inverse operations. So if we're subtracting two matrices, we subtract the corresponding components. Zero minus 1, 3 minus a negative, so plus 1, negative 2 minus 2, 4 minus 1. The next operation is multiplying two matrices together. And this is a little bit different. When you talk about vectors in other math classes, there are different ways to multiply vectors together. With matrices, there's pretty much one standard way of multiplying matrices, but there are only certain type of matrices that can be multiplied together. We'll look at an example. If I want to take this matrix, it's a 2 by 2 matrix. Then whatever matrix I multiply it by has to have two rows. It could have any number of columns, but it has to have the same number of rows as the first matrix has columns. And we'll illustrate why that's the case in a moment. So let's just do a 2 by 1. So in order to multiply these two matrices together, the first component comes from multiplying the first row in the first matrix by the first column in the second matrix. And the way we multiply them together is basically the same way we take a dot product with vectors. We multiply, if I'm doing this row times this column, I do 1 times 3 plus 3 times 1. So again, those I did 1 times 3, then 3 times 1, and I add those together. Now for the row 2, column 1 piece, we take the second row, first column, hence row 2, column 1. So second row, first column, 2 times 3 plus negative 1 times 1. There's not another column to multiply by, so our final answer only has one column, 3 plus 3, and then 6 plus negative 1, 5. So if we want to know before we even multiply the size of the resulting matrix, we said that these have to match in order for us to even be able to multiply, and the size of our resulting matrix comes from the number of rows in the first matrix by the number of columns in the second matrix. So this is a 2-row, 1-column matrix. Now let's observe what happens if we have matrices that the column in the first one and the rows in the second one don't match. So we've got 3 rows, 2 columns. Let's see if we had 3 rows by 1 column, or we'll do 3 rows by 2 columns again. we'll even do the same matrix times itself. So basically squaring it. So in order for us to multiply these together, our row 1, column 1 element would come from taking the first row times the first column, but notice there's a problem. When we take the first row and then the first column, they don't have the same number of elements. We could do that times that, or those times each other and those times each other, but there's not another element to multiply the 0 by. So those two matrices cannot be multiplied together. So that's one thing we have to be careful of. Which brings up a point. Let's see. For this set of matrices, if we call this A and this B, A times B gave us this. But let's look at, well, what about B times A? If we took B times A, notice row times a column, those number of elements don't match. One element here, two elements here, so it's not possible for us to multiply these two matrices together. So what's my point? Generally speaking, and of course there's always an exception to the rule, if you multiply two matrices times each other and then change the order, you don't get the same answer. Sometimes you don't even get an answer for one of them. So multiplication of matrices is not commutative. The order does matter, which is something that's new to us. Things we've done in the past, it didn't matter which order we multiplied. If we took two numbers and multiplied them together, we would get the same thing if we changed the order. That's not so for multiplying two matrices together. So that's one thing we have to be careful of in the future. If I have a matrix and I want to multiply it by something else, let's say matrix D, I can't multiply it on the left side on the left and on the right side on the other side. Generally speaking, that is not equal. So if I take a matrix, if I multiply it on the left, on this side, if I multiply by a matrix on the left side, then I have to multiply it by that same matrix on the left. And again, we'll get into more of that in the future. But we do have to be careful when we solve a matrix equation, which side we put our matrix on. So in the past, solving an equation, let's say we had 1/2 times x equals 3, with just regular numbers, I can multiply by 2 out front on the left side, but multiply by 2 on the right side. Notice this is out front on the left, this is at the end on the right. Those cancel, we get 6, but that isn't the case with matrices. So that is something we have to be aware of in the future. So let's practice. Let's multiply two matrices together again. Let's take matrix 1, 3, 2, 0, 4, 0. And let's multiply that by 1, 3, 0, 3. Oops, can we do that? No, we can't do that. I have 3 rows, or 3 columns here, so I need 3 rows in whatever we're multiplying by. So let's do 0, 1, 2, 1, 0, 4. So just to check, 2 rows, 3 columns, 3 rows, and it doesn't matter how many columns, in this case, 2 columns. So our resulting matrix will be a 2 by 2. Those match, so our resulting size 2 by 2. So row 1, column 1, we're going to put here, we'll do 1 times 0 plus 3 times 2 plus 2 times 0. Row 1, column 2, we'll take the first row times the second column. So 1 times 1, 3 times 1, 2 times 4. So we'll get 12. Again, row 1, column 2. This is row 1, column 2. For row 2, column 1, we'll take row 2 times column 1, 0 times 0, 4 times 2, 0 times 0. So we'll get 8. And then lastly, row 2, column 2 position. So row 2 times column 2, 0 times 1, 4 times 1, 0 times 4. So that's the result of multiplying those two matrices. All right. So let's see. Let's look at an example. Let's suppose we have A equals 1, 2, negative 2, 3, 1, negative 2. X equals x1, x2, x3, and 0 being a column vector with all zeros. That's a 2 by 1. So when we refer to a 0 vector, you have to know what its dimensions are, or even a 0 matrix. But a 0 matrix or vector is one in which all components are 0. Make another quick note and then we'll come back. An identity matrix is a matrix that has is a square matrix, same number of rows and columns, where we have one diagonal, all other entries are 0. And remember that for multiplication in regular numbers, 1 is the multiplicative identity, because when we multiply a number by 1, we get the identical object, the identical number. And all an identity matrix is a matrix such that when we multiply that matrix by the identity, we get the matrix we started with. So if we want a 2 by 2 identity matrix, 1's on the diagonals, all others are 0s. So if we do row and column, we get 1 times 1, 2 times 0. This row times this column, we get 0 plus 2. This row and this column, 3 plus 0. This row and this column, 0 plus 4. Same thing we've got. So again, identity matrix are always square matrices. Ones on the side. And it does turn out that you can multiply on either side by the identity matrix and still get what you started with. Row times column, 1 plus 0. Row times column, 2 plus 0. Row times column, 0 plus 3. Row times column, 0 plus 4. Same thing we started with. So that introduces a couple more terms. That's identity matrix, and over here we looked at a zero matrix or a zero vector. So they give us matrix A, basically vector X, vector 0, and they say solve the matrix equation AX equals 0, which means A times X equals 0. So think about if we were to multiply this matrix by this column vector, we would do row times column, so this would be 1x1 minus 2x2 plus 3x3 equals 0. Then we'd have 2 times x1, 3 times x sub 2, minus 2 times x sub 3. And that equals 0. So this is another way of representing a system of equations without using augmented matrices. We write the coefficient matrix. We use a column vector that is one column that has each variable as its own row, and then our resultant on the right. So if we wanted to solve this system of equations, this is equivalent to having the augmented matrix 1, -2, 1, 0, 2, 3, -2, 0. We'll later see another way to solve this system. Once we reduce this down, we would get 1, 0, -1/7, 0, 0, 1, -4/7, 0. So we have a pivot in the first position, a pivot in the second position. So our third variable is free to be whatever. Our second variable, notice x sub 2 minus 4/7 x sub 3, which is t, equals 0. X sub 1 minus 1/7 x sub 3, which is t, is 0. So x sub 2 is 4/7 t. X sub 1 is 1/7 t. So our answer, our 1/7 t, 4/7 t, and t. Or t is a common factor of all of those, so we can pull that scalar t out at 1/7. Let's see, let's go down. One seventh, 4/7, 1. So for any t that you pick, you can take that scalar times this vector, and that will give you an x that is a solution to this system of equations. For example, if we let t be 7, if we multiply by a scalar of 7, we have 1/7 times 7, 4/7 times 7, 1 times 7. And that is one vector that is a solution. Again, we have infinite solutions because t can be any number, but this is one example of a solution to this system of equations. And let's just look at that and verify that that really is a solution. If we put a 1 in, we get 1 minus 8 plus 7. 1 minus 8 plus 7, which is 0. We get 2 plus 12, 4 times 3, minus 2 times 7, which is 0. So that's one. Really many solutions to that homogeneous matrix equation. So that's essentially what they'll have you do in 2.1. There are a couple other exercises on there that might vary a little bit, but that will essentially get you through 2.1.